We talked a lot about how you're going to prove geothermal works.
Yeah, I would have liked to have sat in on that conversation.
Or the opposite.
Well, maybe we'll just kick things off here and let people join as they can. Today, ladies and gentlemen, we're very lucky to have Dr. Talebkeikhah speak to us. And Mohsen, he holds a bachelor's and master's degree in petroleum engineering from Amir Kabir University of Technology. That's Tehran Polytechnique. And there he collaborated with various research groups in machine learning, geomechanics, and chemical engineering, and contributed to multiple publications. He later received a Swiss Excellence Fellowship during his PhD to allow him to attend the Geoenergy Laboratory at EPFL in Switzerland. And he's focused his research on, and other ventures on, hydraulic fracturing experiments, propagation, and closure analysis, with many publications. And so it's a real pleasure to welcome Mohsen to speak to us today, please.
Thank you. At first, I want to thank John and Igor and also ARMA community for giving me this opportunity to share my results and gaining your feedbacks and comments. Today, I'm going to present a closure analysis of hydraulic fracture in a high leak-off condition, in which we are using a novel aperture measurement technique for measuring the opening at the inlet of the fracture. And afterward, we will do some microscale analysis of the residual fracture that remains inside the sample to check the process zone and the surface behaviors. In the life of every hydraulic fracture, as long as we are injecting high pressure fluids, fracture is going to propagate till we stop the injection, that we call it the shut-in time. After this shut-in time, depend on the regime of fracture propagation, this fracture will going to propagate more, or it stop immediately. And afterward, we will have an arrest period, and also afterward, we will reach to a phase that fracture start to deflate and it start to recess. The focus of my talk today is mostly on the closure part, and why this closure part is important. Accurately picking the closure time and pressure will help us to estimate the leak-off coefficient and also in situ stress. The traditional and typical method that we have for picking the time and closure are mostly the G function methods, tangent method or compliance method, or the other method that is working with the pressure behavior with the different function of the time. But the point is that all of these methods are based on pressure record. Recently, Pierce and Detourne, they developed a new analytical solution. They called it sunset solution. In the sunset solution, they assume that at the very close to the full closure, the leak-off coefficient has a constant value, and they have an asymptote for the opening at the inlet, and they mentioned that opening at the inlet close to the time of closure, it has linear behavior with the reverse time, and reverse time is just real time minus the closure time. And we can also derive from their equation that pressure also has a linear behavior with the square root of this reverse time. So this can be a signature of closure for us, and to check the validity of sunset solution, we need to design an experiment. To designing that experiment, we selected Molasse sandstone from a quarry in Switzerland, which is high porous. The porosity is about 20%, and the tensile strength, it's a kind of a weak sandstone, because the tensile strength, you can see it is maximum 2 MPa, and the Young modulus is around 5 gigapascal. And the reason that we selected such a sandstone for doing hydraulic fracturing is just to speed up the process of the closure. We really want to have multiple cycle of injection and closure, and we want to practically do it in our lab. So we need to have a high leak of sample. So we took a cubic block of Molasse sandstone, which is 25 centimeter in each side, and we are going to drill a well in the middle of the rock, and then we will create a notch exactly at the injection point, and then we epoxy a specific completion tool that contains the opening system, opening measurement system, and also in addition it contains a injection line. Afterward, we put this sample that it contains a completion in the middle. We're putting it inside a true triaxial frame that we can apply a confining stress in 3 principal directions. During the experiment also, we are monitoring the pressure, rate, and volume. Also, we had acoustic monitoring system, but in this case of sandstone, because it is really attenuative, the results were not really good, so I'm not going to present any acoustic result. I'm just going to focus with the pressure, rate, volume, and the opening that is coming from a novel technique that we are using. One of our novelty was a technique that we are using for measuring the opening at the inlet of the fracture. That this method is using electromagnetic induction. For using this method, we need an eddy current sensor. If I want to give you more detail about this eddy current sensor, if we apply an AC current to eddy current sensor, in eddy current sensor there is a coil at the tip of the probe, and as soon as we apply AC current, a magnetic field, which is plotted in blue, is created around this coil. And this magnetic field, with the Faraday law of electromagnetic induction, it will create an eddy current vortex. It's a kind of magnetic field on the conductive plate in front of the tip of the probe. And this vortex magnetic field, this one is also creating another magnetic field that is plotted in red by the Lenz's law of electromagnetic induction. And by superposition of these two magnetic fields, the superposition of these two magnetic fields has a linear relationship with the distance between the surface of the conductive plate and the tip of the probe. So the reason that we select this method is that it is completely independent of the pressure and temperature. Also, it is sealed to any kind of fluid. It has nanometer accuracy, and it has a high sampling rate. And the other The other advantage is that we can directly measure the opening at the inlet of the fracture. And it's a small, it's the maximum diameter of the probe is just 6 millimeter. And because it has thread, we can reuse it for different kind of experiments. There is only one point that all of these magnetic fields, they will impact by different kind of injection fluid that we are using that's surrounding this medium, and also the type of the material that we are using as a conductive plate. So we had to design and manufacture instruments that I am showing it here. In this instrument, the EC probe is EC probe, I mean eddy current sensor. This EC probe is fixed at this position, and then we are going to inject the fluid that we are going to inject in our experiments. And the target conductive plate is connected to the bottom part. This bottom part, we can rotate it. And by rotating the bottom part, this conductive plate that is attached to it will have some displacement in the axis of this cylinder. So during this experiment, this instrument is connected to a micrometer, a big micrometer. So we will have two values. One value is coming from EC probe, and one value is coming from the micrometer. And when we plot it in different pressure, we can see that all of them, they have same slope. There is a little bit offset, and that is because of just displacement in the instrument at that pressure. So for correcting with our injection fluid and the type of the conductive plate, we need to multiply all the values that we have in our experiment by the slope of this figure to reach to the correct value of the displacement. For more detail, you can refer to this paper that is published in October 2024 in the Sensor Journal. And from now on, all the opening measurement that I have in all of my experiments is coming out through this electromagnetic and induction technique. So we were able to successfully do 4 different experiments. Their names are M03, M05, which we injected glucose with the glucose with the viscosity of 62 Pascal second. And also M04 and M08 that we were injecting glycerol with the viscosity of 0.5 Pascal second. After doing some scale analysis that the equations are here, we could easily understand that M03 and M05 that we injected in glucose in those experiments, the fracture regime is a storage viscosity dominated regime. And in M04 and M08 that we were injecting glycerol, the regime of fracture propagation was somehow viscosity leak-off dominated regime, and mostly leak-off dominated regime. So to just save time, I'm just going to present the M03 and M08 from each of these 2 regimes. For the M03, here you can see the result that we have, the opening that is coming from the electromagnetic and induction technique, and the pressure and the rate in the bottom sub-figure. Also, the data is, all the data are in the link below. You can just click on it or reach to the Zenodo file that we have for attached for all of these experiments. So here you can see that the green part is related to the propagation of the fracture till the shut-in time, and after shut-in time, we will have a closure phase. And after the experiment, when we finish the experiment and everything is done, and we also release the confinement stress, we can see a slight change in the middle of the rock, which is just related to elastic deformation of the rock just because of releasing the confinement stress. And the other thing that is really interesting is that you have to see that opening after the full closure, it will never reach to zero. And a kind of residual opening remains inside the fracture. And yes. So when we have the opening at the closure phase and also pressure at the closure phase, we are going to plot them versus each other. Here you can see the opening, and here is the pressure. In addition to all of this, I showed the derivative of the pressure with respect to the opening, that is denoted as a stiffness of the fracture, and in blue. And I could see that at a specific point, we will have a kind of linear behavior and a kink in the behavior of the stiffness of the fracture. So we are associate this point as the point that fracture contact happen, and afterward we will have an elastic behavior after the closure. So we will pick this point as our closure pressure and closure time that we have. And also because we have the pressure record, I also checked the compliance method, that is dpdg versus the g function, and also tangent method, that is dpdg versus g function. And also another typical method that we have, that is just plotting the pressure versus a square root of delta t, which is this delta t is real time minus the shut-in time. I don't know that this is true or not, because I know that in the assumption of the compliance and tangent method, it mostly says that it is working in a low permeable condition. But I could see that compliance method has better estimation of the closure, and our picking point from this figure that is working with a stiffness is consistent with the compliance method that we have as a classical method for picking the closure. But for the tangent method or the other methods, no, they are giving us a value far away from the what we expected. So we have the peaking point, we have the peaking pressure, and we have the contact pressure and contact time. So we can check the sunset solution that Pierce and Detournet developed, and we could easily see that the opening asymptote is really linear where it is the time of the full closure. And we can see that opening at the inlet of the fracture has linear relationship with the reverse time. And also here we can see that opening has a residual opening. And this offset is because of that residual opening. And also for the pressure asymptote of sunset solution, we can see that the pressure at the inlet of the fracture, it has a linear behavior with the square root of the reverse time. And this is interesting because we could see the analytical solution in our experimental results. So now it's time to check the other experiment that has been done with by injection of glycerol with lower viscosity than the previous experiment. In this experiment, we did 7 cycles of injection and closure, injection and closure, injection and closure. And let me say to you that after all these 7 cycles, fracture remains inside the block, and it didn't reach to the boundary of the sample. Here also we see this residual opening that remains inside the fracture even after the experiment and even after we release the confinement stress. I want you to have an attention to the pressure values. As I mentioned to you, here we have a vertical confinement stress of 8 MPa, and the tensile strength was some value about maximum 2 MPa. But for breaking this rock, we needed a value about 30 MPa. That this is just explained by the huge back stress that is happening during the experiment. That let me show it here, that you can see that this is when fracture is propagated. This is after the experiment when we cut the sample, and because we had some fluorescence additive, we could visualize the fracture path after the experiment, and it is under UV radiation, and we could see that fracture propagated, and there is a high leak of area around the fracture, and this high leak of area will create a huge back stress that cause that for breaking this rock we need such a pressure to break the rock. So here for each cycle, I plotted the stiffness versus pressure for each cycle, and we could see that, as I mentioned before, there is a kind of linear behavior in the stiffness exactly at a specific point, at a specific king point. We can see a linear behavior, especially on this cycle. You can see it is exactly linear. Here it is completely linear. And one thing that is really interesting is that all these stiffness value, they are in the same order and close to each other. Although they are different cycle with different rate of injection, all values are constant. So also I plotted the pressure asymptote at those peaking points for each cycle. I plotted the pressure asymptotes of Sunset solution, and we could see the linear behavior in the linear behavior of the pressure at the inlet with the square root of reverse time. Also for the opening asymptote, we can see the opening at the inlet has a linear relationship with the reverse time in each cycle. Also, I checked the classical methods. Here you can see the tangent method. However, I don't like the peaking with the tangent method because it will give us a value that it is unexpected. And also the other method of pressure versus a square root of delta T is the value that it gives to us. It is not really expected, but the compliance method, however, we have a high leak off and permeability is high. It is consistent with the value that we peak with the stiffness figure. So overall, if I want to compare all the experiments, in M08 and M04, we injected with glycerol, and in M03 and M05, we injected with glucose with higher viscosity. At first, let me show you here in this figure. These are the peaking contact pressure for each cycle. You can see that for both of M08 and M04, that's we were using lower viscosity fluid, the peaking pressure points are higher than the vertical confinement stress at those experiments. However, in M03 and M05, the contact pressure for that peaking point is a value around and in some cycles they are a bit higher than the vertical confinement stress that we have. And but the residual opening that we have at the closure. For M04 and M08 with lower viscosity, it is a lower value. And this 5 micron is value close to our particle size. And M03 and M05 that we were injecting glucose, the residual opening at the closure, it is a value somehow bigger than the experiments with lower viscosities. And so let me repeat it again, that when we are injecting lower viscosity, with lower viscosity, we will have higher contact pressure, although its residual opening is smaller. But when we are injecting higher viscosity fluid, the contact pressure is smaller, but the residual opening at the closure is bigger. And this is a strong effect of back stress that we have from the pore pressure that is induced around the fracture. And at this figure, you can see the stiffness value for each cycle. That you can see that for all 5 cycles of M08, they have the same value, and it is close. It's interesting that these 2 experiments are different experiments, but same fluid, and the value of the stiffness for each cycle, they are close to each other. And also M03 and M05 that we were injecting same fluid, they have somehow same value for the stiffness at the peaked time and pressure. Okay. From now on, I'm going to present the microscale analysis on the 2 experiments of M03 and M04 from different regime of propagation. So after the experiment finished, let me say to you that in fracture in none of our experiments reach to the boundary of the sample. And fracture at the end reached to the half of the length of the sample. So what we did was that we drilled a core from the boundary of the sample till inlet of the fracture. And fracture, you can assume that fracture path is up to half length of this core. So the core will keep the residual fracture as it is. So we will send these 2 core samples from each of these experiments to CT scanning, and we did CT scan perpendicular to the surface of the fracture every 10 micron with the step of 10 micron. So here you can see that, here you can see for both experiments, you can see that the CT scan is going from the, it's going and it reached to the tip of the fracture, and it's going and it's getting close to the inlet of the fracture, and the fracture size is going, and the residual opening is going to increase and increase. Okay, at the end you can see also the notch here. So this will give us an idea that by knowing the size of each pixel in this image, which is 10 micron, we know it from our CT scanning, we can estimate, we can reconstruct the fracture surfaces, both upper and lower fracture surfaces. That's so we reconstruct both upper and lower fracture surfaces for both experiments. And by having these upper and lower fracture surfaces, we can, by subtracting these 2 surfaces from each other and having a specific threshold, we can reach to some red points along our fracture surface, that these red points are the points related to the contact and breach points along the fracture surfaces. To knowing what are these red points exactly, I brought the CT scan images at those specific red points that you can see them here. For both experiments, the bottom row is close to the fracture inlet, and the middle row is in the middle of the fracture, and the first row is close to the tip of the fracture. And here you can see that as much as we are getting close to the tip of the fracture, we can see some unfractured and breach points. For example, here fracture completely disappeared, or here fracture is not connected. Also here fracture is not connected. Here fracture disappeared. Here it is connected, but it is lower than the resolution of the CT scan image, that we assumed it as contact point, not as a breach point. Here also it is the kind of contact point, but here, interestingly, it is close to the inlet of the fracture, but the fracture at this cross section, it is not connected at this point. So we can say that these red points are belong to the contact points, and also the points that are unfractured. So if we count the number of these red points along the location of each rows, we can reach to these two figure here when we are counting the number of these red points, and we could see that exactly at the specific point or a specific distance from the inlet of the fracture, about 0.7, there is a point that density of these red points is going to increase suddenly, that we associated as the process zone. And in parallel, also, we did some calculation of autocorrelation, Pearson correlation value that we all know it as R square, and also autocorrelation decaying slope, that the Pearson correlation coefficient exactly at the time that we are reaching to this process zone, it's going to deviate from the one value, that it shows that the correlation is going to decrease. And also the decaying slope of the autocorrelation is going to increase in negative range. This means, what it means is that the correlation between two surfaces is going to vanish faster, exactly at the time that we have this process zone. And also we calculate the Hurst exponent for each CT scan, and along the fracture propagation direction, we can see that we will see a huge perturbance when we are reaching to this process zone. And we could see this for both experiments. So the main reason that we have a residual opening after the experiment are presence of these contact and also unfractured or breach points. That at the end, I could also profile the residual opening that we have from the inlet till the tip of the fracture. But at the close to the tip of the fracture, I will lose the resolution, so it will not reach to the 0 at the end. But for both experiments, we could show the profile of opening, residual opening that remains after the experiments. And we checked also that this Hurst exponent, one time in the direction of the fracture propagation and another time perpendicular to the direction of the fracture propagation. And we could see that the value in both directions, they are somehow close to each other. So we can see that fracture surface is somehow isotropic. And at the end, we know that this, as we showed here, that Hurst exponent is somehow a value close to 0.4. We saw a lot in the literature that people mentioned that in sandstone sample, fracture goes along the porosity and not through the particles, but it will going surrounding the particles. And they say that this behavior happens when the Hurst exponent is close to 0.4. And they also mentioned a universal value of 0.8, and they showed that this behavior happened in a crystalline rocks and materials or glass or metals. And they said that this 0.8 happened when fracture propagate transgranular. For checking that, we did another CT scan with higher resolution to better detect the fracture path and also the particles. And we could see that really fracture goes through the porosities and not it is not breaking any particles. Here in the bottom figure, we can see from the Aviso software that it detects by segmentation, it detects the particles, and we can see that none of the particles are broken. The point is that we asked for a scene section analysis, but up to now I don't have the result to show it, but I can have the result, I think, by the next 2 weeks. And in summary, we could successfully develop a method of electromagnetic induction for measuring the opening at the inlets. And then we could do several successful hydraulic fracturing experiments with multiple cycle of injection and closure. All the data sets are valuable, and they are easy. We can easily access to them through the Zenodo links that I provide them. And also, we showed that fracture will never close. And our measurement of fracture opening allows a better estimation of the closure than pressure alone. And this kinking the measured stiffness value is a robust technique for picking the closure time and pressure. And it is consistent with the compliance method that we had before. And the time evolution of opening and pressure close to the closure follows the analytical sunset solution. And also we showed a strong backstress behavior that we have. On the microscale analysis, we could reconstruct the fracture surfaces, and we could have the distribution of the fracture contact and breach points. And we could show the process zone due to the points that we have a high density of these contact and breach points. And we could check that the fracture surface is isotropic, and we could also show the intergranular fracture propagation nature. Yeah. And thank you all for listening to my talk. I am open to all of your questions and also open to any collaboration. Yeah.
Mohsen, thank you so much. Just a spectacular set of experiments. I encourage people to send their questions to the chat. We already do have a couple from Jihao Wang, and his first question relates to the backstress that you pointed out, and whether you did any estimation of what the magnitude of that backstress was, and my question is, does it correlate with theoretical expectations?
First of all, we need a pressure-dependent Leakoff model to check, because it is what we found is that it is not observing the LEFM that we have normally, and we cannot use those techniques because we can see a huge backstress about 20 megapascal that is occurring during our experiment, and this 20 megapascal is the deviation from the normal LEFM that LFM equations that we have normally with the Carter Leakoff assumption.
So just to put that into perspective, the follow-up question from Jihao was what is the fluid pressure required to open the fracture in the test in the viscosity storage regime versus the leak-off regime?
I think I have in the viscosity dominated regime, we just needed about, let's say, 15 to 20 MPa in the viscosity dominated regime. But interestingly, when we have leak-off dominated regime with lower viscosity, this value goes to 35 MPa.
Okay, we thank you. Thank you. We also have a question and comment from Mark McClure, and Mark's comments kind of long, so I'm going to ask Mark if he can. I don't know
Sure.
whether he can unmute himself, but if so, just go ahead, Mark.
Yeah, sure. Thanks, John. Happy to. First off, really impressive. This is I've never seen a work quite this sophisticated on this topic. It's great. I wonder
Thank
if
you.
you're going to do this in low permeability formations, because if I understand it correctly, I think the sunset solution assumes that there is no leak off from the parts of the fractures that are closed. And my expectation would be that in low permeability, the closed parts of the fractures remain dimensionless, high dimensionless conductivity because the permeability is so low. And so leak off would continue to occur from the closed parts of the fractures. So if I understand that correctly, and maybe I misunderstand the solution, I would wonder if it would not match low permeability data. And my related question is, I don't know, does the sunset solution account for this residual aperture that you are showing?
Yeah, this is completely true. I do agree with you that we have some contradict with the sunset solution assumption, but somehow I saw a paper from Anthony Pierce that they showed that they could see this sunset solution when there is propagate, and we can assume that this propagate can have the role of this residual opening. Yeah, but I do agree with you. We have some contradict with the sunset solution because sunset solution mentioned that we do not have any opening after the closure and it just closed completely. Yeah, but what we can see from the experiment is that there is a residual opening at the end of the experiment.
Thanks. But do you plan to do this in low permeability?
I personally, I do not have plan to do that.
Yeah. This is more than enough for a PhD.
My PhD finished, but I am happy to do that. Yeah, and also we have planned to do the experiments in the geoenergy lab in the saturated condition.
Cool.
Yeah.
Cool. Well, thanks again. Really impressive. Great work.
Thank you, Mark.
So we have one request from Mohammed Mohsen, and that's if you would go to the high leak off cases, the G function plots, etc., and explain a little bit more on how you determine closure. And his interest is comparing the compliance and the tangent method, and why the compliance method is more representative.
From the compliance method here, you can see in the high leak off condition, what I could see is that we need to, I think Mark can correct me if I am saying it wrong. We need to check as soon as the pressure is going downward, and we need to plot, let's say, a tangent point. And if I want to peak that point, this point will be somewhere around here, maybe, but or on this part, I cannot really, I can, on some cycles, I cannot really see it. For me, the tangent method, I'm not sure that I can use it or not. But the compliance method, as we know that it mentioned that it should be 10% higher than the minimum pressure, and we should have also we should also assume a value and an offset value for the roughness of the fracture. So the peaking point, sorry, not this one, this one is the for the compliance method. The peaking point is somehow closer to the value of a stiffness method. Yeah, and this is the reason that I'm saying that the peaking point from the stiffness method, it has a closer values to the one that we have from the compliance method. I don't know that I answered your question correctly, or
Mohammed, did that make that clear?
Thanks, Mohsen. Yeah, almost, but but we can get the data and do more analysis on them by the tools that we have, and see better like how the closure can be picked. Usually, like in the first derivative, the very first zero slope that we see usually shows the compliance, and the second slope, zero slope, shows the tangent method. It's hard to pick from this data.
So
also maybe it is good that Mark say that is it correct to because this point I'm also a little bit, I have doubt that can we use in high leak-off condition although I can see that it is consistent with the compliance.
Well, I think one thing that's maybe a little bit confusing is normally the derivative is plotted as positive, even though it's actually negative. So that is a little confusing, that all these, I think what you're showing as the lowest point is the most negative derivative. That's actually the highest rate of fall off, right? So like all those orange lines, so the derivative plot, you're correctly showing that it's a negative derivative, obviously, but traditionally it's plotted as if it was positive. So it actually would all be flipped. It would look.
I see. Different. Yes, you're right. Yeah, I see that right.
But yeah, I mean, the essential concept of the compliance method is that there's going to be a point where the pressure fall off accelerates. And so like if we look in the top left corner, you can kind of see that there's a certain slope at if you look at blue, like the blue line, there's a certain slope, and then very soon it steepens. So the contact point would be picked essentially at the point where it steepens.
Yes.
Now, also in high permeability formations, sometimes you really just don't see that at all. And then the recommendation is just to basically use the ISIP or assume that it closed rapidly.
Yeah.
But like the tangent method, can you go back to the tangent method plots?
This one.
Yeah. So these are also a little bit confusing to read because it's plotted negative. So if you plotted all these curves as the absolute value of dPdG, the shapes would look different. So just make sure, like in I don't know, in panel B, the tangent pick is probably around a G time of like 0.9, 0.8.
Yeah, this.
Yeah. Yep. Okay, thanks.
Yeah, but if we select it at these points, because it will deviate a lot from the compliance and also the stiffness contact point that we have.
Yeah. I mean, it does tend to be lower. But yeah, just want to clarify that you probably should plot it at the absolute value of dPdG. That's the standard convention.
Okay, that was a good point. Thank you.
So no more questions, but I think that the message is that this is going to be a great thesis, lots of publications that are associated with this, and the data should be available for conversations with Mohsen or with Brice. And I want to thank everybody for joining. Just a fantastic set of experiments, Mohsen. Congratulations.
Thank you all.
So we'll see everyone in a couple of weeks.
Yep. Yeah.
Yeah, these were really outstanding. I mean, just very carefully done. That's so great.
Thank you, John. This is your kind comment. Thank you.
No, I'm glad you presented them.